This lecture is about algorithm W for type reconstruction. So the specification for the algorithm W is it takes typing context gamma and expression E and returns type substitution S and the type for expression E. And the soundness property of this algorithm W states that if this is the case, then under this typing context, substitution S applied to typing context gamma, expression E as type A. So now let's develop the algorithm W, but before we provide the details, let's review the whole problem. So this is the syntax for the language. The language is based on left polymorphism or implicit polymorphism. So we have two categories of types. Monotype. Monotype A is this function type or type variable alpha. And we have a polytype, which is this monotype or is for alpha followed by another polytype. So according to this definition, a polytype can be written in this form for all alpha 1, for all alpha 2, and so on for all alpha n, followed by monotype A, and we call this one as a Prenex form. And expressions are variables, lambda abstraction, application, and this left binding. And that's all. And values are just lambda abstraction. Typing context. Typing context gamma is either empty or an existing typing context gamma extended with new type binding. So notice that unlike the previous formalism like left polymorphism, we don't have this type variable declaration in the set of typing context. And the reason is, in the development of this algorithm W, we will generate only valid type variables. We will never generate invalid type variables for the simple reason that there's no need to. So we don't use this type variable declaration here. And let's review the typing rules. For variables, we have to have corresponding type binding in typing context gamma. Then its type is U. Notice that here, variable x can assume a polytype in general, because even though this variable from lambda abstraction can have only monotype, this variable from left binding can have polytype. And what about lambda abstraction? Here, we have to make a guess on the type of this variable x. So let's just say our guess is type A, so x has a type A. And if expression E has a type B, then this one has a type A arrow B. And what about application? If expression E has a type A arrow B, and then expression E prime must have the same type over here. So the whole application has type B. And what about left binding? So first, we want to type check this expression E. So in general, this expression E can have a polytype. So let's just say expression E has a type polytype U. And then we have to decide the type of this expression E prime under the extended typing context, where x has now type U. And under this extended typing context, expression E prime has type A, then the whole left binding has type A. So this is the typing rule for left binding. Now what about the generalization rule? Suppose that expression E has a type U. Now we'd like to generalize this type to something like a for alpha U. So we introduce a fresh new type binding, new type quantifier for all alpha. And in order to justify this generalization, you have to make sure that this alpha is not in use in typing context gamma. Perhaps alpha is found in type U, otherwise there's no need to apply this generalization rule. So suppose that alpha is found in type U, and if alpha is not used in typing context gamma, then you are free to apply this generalization rule to generalize the type to this polytype. So here's an example. So suppose that you have lambda x dot x, and maybe it has a type alpha arrow alpha. And furthermore, assume that alpha is not found in typing context gamma. So in typing context gamma, alpha is never found. Then, intuitively, lambda x dot x has alpha arrow alpha. But that means that it has actually a polytype. You can assign polytype to this lambda abstraction. So in this case, you can apply this generalization rule and deduce it has type for all alpha, alpha arrow alpha. So that's an example of applying this generalization rule. So notice that alpha should not be found in typing context gamma as a free type variable. And the last typing rule is the specialization rule. What it says is, suppose that expression E has a type for alpha U, then we'd like to specialize the type variable alpha to a concrete type, such like a bool or int, or another type variable beta, and so on. So you are permitted to specialize it to any type A for alpha in type U. So here's an example. Suppose that F has a type for alpha, alpha arrow alpha. And in order to use this variable F in lambda application, it should be assigned a monotype. So for instance, we might choose to assign bool arrow bool, which is a special case of this polytype, or we might choose to assign int arrow int to this variable F, because this is a special case of this one. So these two instantiations are fine, but what we see in the design of algorithm W is whenever you have a polytype like this one, then you apply this specialization rule and instantiate this type variable alpha to fresh type variable, something like this. So here, beta arrow beta is monotype, so this application of specialization rule is legitimate. And furthermore, theta is fresh. And this is fine because every type variable that we generate is guaranteed or assumed to be valid. So these are all valid examples of applying this specialization rule. So in the algorithm W, we will not see something like this one, but we will see actually the last case where this type variable alpha is instantiated to a fresh type variable beta. So that's actually the specification for this algorithm W. So this is the input specification, and we'd like to devise an algorithm W with this specification. It takes as input typing context gamma typing context gamma and expression E, and it returns a substitution S and monotype A, and it satisfies this property. And we also defined this type substitution. So type substitution S is either identity substitution, which has no effect on type variables, or singleton type substitution, or composition of two type substitutions. So this is the definition of type substitution, which we need in this algorithm W. Now, let me give the details of this algorithm W. Because there are 4 cases of expressions, we need 4 clauses. So we need 4 cases. Variable case is the first case, and the second case is it's a lambda abstraction. That's the second case, and the third case is the expression is this application, and the last case is this expression is left binding. So let's go over each case. So let's start with the first variable case. So what is the algorithm W for this variable? So in order for this variable to be well typed, you have to have a corresponding type binding in typing context gamma. In other words, you must have this type binding of this form in typing context gamma. Otherwise, this fails to type check. That is, if you don't have type binding x:\new in typing context gamma, the algorithm returns by reporting fail. So let's assume that x:\new is a member of this typing context gamma. And let me expand this U in this form, in the pre-next form. So we have x:\, for all alpha1, for all alpha2, for all alpha n, A. So this is currently found in typing context gamma. And then what is the substitution? And what is the type that we can assign to this variable x? And it turns out that this is where we actually apply the specialization rule. So to illustrate why we need the solution to be shown shortly, let's consider this example. F applied to 0, F applied to Boolean constant true. But this is the prototypical example where we introduce a polymorphic expression. So perhaps F is going to have type for all alpha, alpha arrow alpha. And here we use this polymorphic expression really polymorphically in different way in different contexts. Here, perhaps we will specialize the type of F2 into arrow int, and here to bool arrow bool. Now, the case shown over here is with the analysis of the first variable f, the first instance of variable f here, and also the second instance of a variable f here. So let's consider the first case. So here, now we have just applied the algorithm W with some typing context with an expression f. And this expression f points to this one. And we know that f has this polytype. Then what is the best action that we can take? If we are lucky, we could just assign int arrow int here. For instance, some oracle could tell us the right way to instantiate the type of variable f is to instantiate to int arrow int. In this case, later we will find ourselves lucky because the argument happened to be of type int. And what if the second case? So now we are making a call to this algorithm W with expression f, where this expression f is pointing to the second instance of variable f. In this case, because we eventually typecheck a lambda application, this f must be assigned a monotype. And we could choose, for instance, bool arrow bool. And also in this case, we are lucky because this is the right choice. The argument happens to have a type bool. But this is just a coincidence. We have not analyzed the argument, this integer and this Boolean constant true yet. So at the time of analyzing this function f, this variable f and this variable f, we have no idea what would be the type of its argument. So the best action, the most conservative action, or the safest action we can take here is we just leave the type of this variable f unanswered, unknown. That is, we don't know the actual type, but it must have this form, something arrow something. So, but we don't have a notation like this question mark, but the idea is when we are type checking this variable f, we have to specialize it to some monotype, but we don't want to specialize it to int arrow int because we don't know the type of the argument yet. So what we do is to introduce a fresh type variable f, another fresh type variable. So let's just say fresh type variable, a beta, and then assign beta arrow beta here. And later, we will compare the type variable beta with the type of the actual argument int. And later, we will perhaps generate this substitution int for beta. So it is safe to introduce a fresh type variable beta and assign beta arrow beta to this function f. So that's the basic idea. So what we do here is, it is always safe to specialize all these type variables to fresh type variables. Let's just say we introduce fresh type variables beta 1, beta 2 through beta n. And then what happens is we instantiate the alpha 1 to beta 1, alpha 2 to beta 2, and so on, all the way down to alpha n to beta n. In this way, we don't have to make a guess on the type of the concrete type for this type variable alpha 1, alpha 2, and alpha n. Later, when we actually compare these type variables against the actual argument, at that time, we will decide the actual value, the actual type, the concrete type for all these type variables. So the plan now is we introduce fresh type variables, just as many fresh type variables as there are type quantifiers. And then we just return this resultant type. So the answer is there's no type substitution. So it's identity substitution. And the real type is use beta 1 for alpha 1 and use beta 2 for alpha 2 and use beta n for alpha n. Use beta n for alpha n in type A. But you have to make sure that all these type variables, beta 1, beta 2, through beta n, these are all fresh type variables that they have never been introduced before. then this is the safest action, the most conservative action that you can take in order to deal with this variable. So this is the first case. What about the second case? The second case is typing context gamma with lambda abstraction. So now you have to find a type substitution and the resultant type for this lambda abstraction. So here, we don't know the type of the best type that we can assign to variable x. So for instance, if the argument is something like integer 0, then x could be assigned the type int. But the problem is, we are just focusing on this lambda abstraction and we have not analyzed the argument yet. Or even if we have analyzed the argument, the result of analyzing the argument is not passed to this function call. So therefore, we don't want to finalize the type for this variable x. Instead, we just leave it as a question mark. We don't know what the type is. And in order to express our decision, we don't know the type of this variable x. We introduce a fresh type variable alpha. So we introduce a fresh type variable alpha, and now x is going to have a type variable alpha. So that's the plan. Now x has a type alpha, and it's time to decide the type of this expression e. So the typing context is now typing context is the gamma extended with this type binding x colon alpha, and we have to find out the type of expression e. So what we do is, now it's time to make a recursive call to this function, this algorithm w, because we are analyzing the given expression structurally. So the typing context is this, and the expression under analysis is expression e. So therefore, we make a recursive call. So first, we introduce a pressure type variable alpha, and then we make a recursive call. Let's suppose that this recursive call returns type substitution S and monotype A. Okay, so to summarize the story so far, what we do is, given a typing context, the gamma and lambda abstraction, what we do is we first introduce this fresh type variable alpha, and then we make a recursive call to the algorithm w. And suppose that this one returns type substitution S and monotype A. If this call to algorithm w reports to fail, then the whole type checking fails. Then let's interpret this one according to the invariant or the soundness property of this algorithm w. This result means under typing context S applied to gamma and x with the type S applied to alpha, expression E has a type A. So if we go back to the specification here, we just reinterpreted the result according to this statement. Then by the arrow introduction rule, under typing context S gamma lambda x dot e has a type S alpha arrow A. So now we are ready to extract the final answer. The substitution is this one, S, and the type of this lambda abstraction is this one. So let me write it over here. This one goes here, S alpha arrow A. So this is so for this lambda abstraction case, first introduce a fresh type variable, and second make recursive call to the algorithm W, and then then pass the substitution, type substitution, and return this type as alpha arrow A. So that's the second case. Now let's talk about the third case. So first, the typing context is gamma. So you want to find out the type of expression E1. So what you do is you make recursive call. So first, call this algorithm W with E1. And suppose that this one returns, let me write it over here. So first, make recursive call to algorithm W with expression E1. Let's say this one returns substitution S1 with type A1. Then according to the soundness property of algorithm W, the result implies that S1 applied to typing context gamma, under this typing context, expression E1 as type A1. So now we have to use this updated typing context S1 applied to gamma instead of gamma. Now it's time to analyze the second expression E2. So next, we make another recursive call. This time the typing context has been modified to S1 applied to gamma instead of the original typing context gamma. So let's use this updated typing context S1 applied to gamma. Under this typing context, the expression E2 produces, let's say, type substitution S2 and return type A2. Again, according to the soundness property of algorithm W, we can interpret the result as under typing context S2 applied to this one, S1 gamma, expression E2 has a type A2. Okay, now we have updated the typing context once more. In the beginning, you had S1 applied to gamma, and now the typing context is S2 applied to S1 gamma. So now we have this typing judgment. And we have to, and in order to decide the type of the whole application E1, E2, we want to use the typing context in a consistent way. That is, this typing context needs to be set consistent with this typing context. So what we do is we apply type substitution S2 everywhere. So we apply S2 here. That means S2, S1 gamma, expression E1 has S2, A1. So what we did here is we simply applied typing context type substitution S2 everywhere in this typing judgment, and then we obtain this one. Now this typing judgment and this typing judgment use the same typing context. So now we are ready to move on. This one is. So now we'd like to exploit these two typing judgments. And now what we should do is, so the typing context we have produced so far is S2, S1, gamma, and expression E1 has type S2, A1, and expression E2 has type A2. But we are looking at this lambda application. So in order to assign a valid type to this lambda application, the type of expression E1 must have this form, A2 arrow something. Otherwise, the whole expression fails to type check. E1 is applied to expression E2, so therefore, it must have this function type, and moreover, the argument type must be equal to the type of the argument. So now, our intuition says we have to solve some sort of equation here. We want to solve S2 A1 is something like A2 arrow something, and we'd like to find out this one. So in order to solve this problem, we introduce another auxiliary algorithm called unify. This is the result so far. So we introduce this unify algorithm, which takes a type equations. So the definition of type equation. So basically, it takes a type equation. This is called type equation of the form left side monotype A and the right side monotype A prime, and it generates a substitution S. And the specification is, if this is the case, you apply type substitution S to A and type substitution S to A prime, then these two guys are identical. And later we will see that this algorithm unify actually takes a set of type equations. So not just a type equation, but it actually takes as input type equations. But the idea is the same. So for example, so it takes a series of type equations like A1, A1 prime, A2, A2 prime, and AN equals AN prime. And then what it does is it analyzes this set of type equations and produces a substitution, type substitution S, and such that S applied to A1 is precisely S applied to A1 prime, and so on. So let's see a few examples which will clarify the whole idea. So for example, the first example is a unify of alpha equals int arrow alpha. So how do we unify the left side and the right hand side? So perhaps there is no way to unify the left side and the right side because the right side is strictly larger than the left side. It includes the left side, namely alpha, and in addition, it has int arrow alpha. So no matter what kind of type you actually assign to this type variable alpha, there is no way to unify the left side and the right side. So this algorithm fails. And what about this one? Unify alpha equals alpha arrow alpha. And similarly here, the right side is strictly larger than the left side. It has alpha, the left side, and in addition, it has this function symbol, function arrow symbol. So therefore, the right side is always larger than the left side, and there's no way to unify the two monotypes. And what about unify alpha arrow alpha against int arrow int? And this is easy because you can just substitute int for type variable alpha, in which case this guy becomes int arrow int, which is the same as the right hand side. So the result of applying unifying algorithm to this type equation is this type substitution. And what about this one? Unify alpha arrow beta equals beta arrow alpha. And this example illustrates that the result of this unification algorithm may not be unique, but all the unification algorithms produce the same result. So in this case, you could choose either alpha for beta. In this case, well, beta becomes alpha, this beta becomes alpha, so the left side is alpha arrow alpha, the right side is alpha arrow alpha. But this is not the only solution. Alternatively, you could choose beta for alpha. In this case, alpha becomes beta, so alpha becomes beta, alpha becomes beta. So the left side is beta arrow beta, the right side is beta arrow beta. So this way we can unify the left side and the right side in one of the two ways. And the last example illustrates that this unification algorithm can take, in general, a set of type equations, not a single type equation. So for example, alpha arrow beta equals beta arrow alpha, and alpha equals int. So this is the first type equation. This is the second type equation. So this unify, in this case, this algorithm unify takes two type equations as input. So in this case, the solution is, so for example, alpha should become int. So alpha should become int. From we analyze this type equation, which will produce this one. And then let's apply this type substitution. Then this becomes int arrow beta, and this becomes beta arrow int. And the remaining solution is use int for beta. So these are examples of using the unification algorithm. Now, let's suppose that we have developed this unification algorithm. And then what happens? What we do now is we know that expression E1 has S to A1, but we should be able to unify this type against this function type. And at this point, we don't know the resultant type, so we leave it unanswered, or we introduce fresh type variable. We introduce fresh type variable alpha here. And then what we do is we call this unify. E1 has a type S to A1 must be of this form, A2 arrow alpha. If this unification fails, then the whole type checking fails. There's no way to assign a valid type to this expression E1 applied to E2. But suppose that this one returns substitution S3. If this unification algorithm returns successfully with type substitution S3, then these two types are indeed unifiable under this type substitution S3. So what that means is that S3 applied to S2 A1 is actually equal to S3 applied to A2 arrow S3 applied to alpha. Now we have this equation. Then what is the final type? Now we are ready to return the final type substitution and the final type. The expression E1 has S2A1, which is A2 arrow alpha. And as the result of unifying this type with A2 arrow alpha, we obtained this type substitution S3. So E1 has now this type. This is the type of so this is the type of E1, and this is the type of E2. So the final type is S3 alpha. And we just accumulate all the type substitutions produced so far, which is S1, S2, and S3. So we return the composition of these type substitutions. So that's the story. So let me go over the story again. So first, we make recursive call to algorithm W with argument E1. Let's say this one returns S1, A1. And then we updated the typing context with the S1. So under this updated typing context, the expression E2 returns this type substitution S2 and type A2. Now the typing context is this one, and E1 has this type, and E2 has this type. And in order for the whole Lambda application to be well typed, expression E1 must have this form. So we call this unification algorithm with this type equation. If this unification algorithm returns type substitution S3, then E1 has this type or this one. So the return type is going to be S3 alpha. So the return type is S3 alpha, and the type substitutions accumulated so far is written this way. So this is how we type the expression E1, E2 under algorithm W. Now the remaining problem is, how do we define this unification algorithm? And it turns out that the unification algorithm itself is quite straightforward. So unify, it takes as an argument type equations, and it returns type substitutions. And type equations E is either empty or existing set of type equations extended with new type equation. So in other words, this is just a bunch of type equations of this form. A1 prime, A2 prime, AN prime. And if this unification succeeds, and if the unification returns this type substitution S, what that means is that SA1 is really equal to SA1 prime, and so on. SAN really is equal to SAN prime. So let's develop this unification algorithm. First, what if the set of type equations is empty? Then you don't have to change any type variable. So the result is this identity type substitution. Next, what happens if we have this type equations E, and the last element is alpha arrow A, and the situation is completely the same as the last equation is A is equal to alpha. So what does that mean? So first, we test if this type variable alpha and this monotype A are equal. So for instance, A could be alpha, in which case we simply return. So the first thing to do is to test if this type variable alpha and monotype A are equal. So if alpha is equal to A, then we have already a type equation. This type equation is already valid, so there's no need to further consider this type equation. So in this case, we simply proceeded to unifying the remaining type equations. So in this case, we just return unify E. So let's say here, we make a recursive call. Next, we test if this A is strictly larger than alpha. So for instance, when we try to unify alpha against integer arrow alpha, and there's no way to unify the left side and the right side. So in this case, this unification algorithm should fail. And the way that we test if this is the case is, we check if alpha is actually a free type variable in A. And if this is the case, first, A is not equal to alpha because we have this first case. Because we have moved on to the second case, if this is the case, that is, alpha is found in type A, that means that A is strictly larger than type variable alpha. So there's no way to unify. So we just report fail. Otherwise, we are ready to produce type substitution, which is A for alpha. So let's apply this type substitution. Then what happens is alpha, so we have this one, and we apply this type substitution, then this stays the same, and alpha becomes A. So now the left side is equal to the right side, so this is gone. So the remaining problem is unify type substitution A for alpha applied to E. So this is the unification algorithm. So to summarize, the third case where expression is this lambda application E1 applied to E2, you will have to make recursive calls to algorithm W twice. And then you will have to call this unification algorithm once. Finally, you collect all the results and return this one as the final result. The accumulation of all the type substitutions produced so far, and this one. And notice that you introduce a fresh type variable alpha here.